And I want to sort of tell you about the physics that's being done here at CERN and hopefully motivate you to learn more or maybe come visit at some point. I'm going to start with the physics story, and in particular, I want to jump in with a brief journey through some different length scales. So I think as a scientist and as a particle or a nuclear physicist, it's very useful to organize the world in terms of different length scales. And I've started here with the length of about 1 meter. And this is about the height of a person. Most people are between 1 and 2 meters tall. And this is because the size of humans, it's also sort of the scale of our everyday experience. So we have a lot of intuition about how things work when it comes to a distance of a meter. If I keep going to smaller length scales, in fact, it's also no problem for us to really visualize a scale that's a factor of 1,000 smaller. Here I've jumped from a meter down to a millimeter, the length scale of sand. But again, at this scale, we can see the sand particles with our own eyes, and we have a lot of intuition about what would happen if you kick sand on the beach or drop the particles from your hand. But this is already where our intuition starts to slow down, because if I keep wandering to smaller length scales, our eyes can no longer allow us to understand, and we have to rely on scientific tools. And this gets into the idea of a microscope. Here I'm showing the scale of 10 to the minus 6, the micrometer, and this is sort of the length scale of bacteria. And indeed, if I even go down another factor of 1,000, we get down to the size of a single molecule. This is just a single glucose molecule. You see here the simple structure. But even this scale of 10 to the minus 9 is much, much larger than anything of interest to my research or to Raoul's interest, and much larger than anything of interest to CERN. So let's continue the journey down to even smaller lengths. If we go down just one factor below the sugar molecule, we get down to the size of an atom. This is the famous Bohr radius, and here is a cartoon for hydrogen. You can imagine hydrogen as this dense positive core. This is the proton, and an electron distributed somehow around it. And the size of this electron cloud is 10 to the minus 10. Remarkably, the proton inside of that is smaller, not by a factor of 10 or 100, but by a factor of 10,000. So one analogy you'll often hear is that if you think of the proton with the electron cloud, it's like a marble in the middle of an enormous football stadium. And so we have this dense positive charge with this negative somehow very far away from it. And 10 to the minus 15 meters, this is what we also call the femtometer, this is getting down to the size that we are interested in here at CERN. But in fact, we can go farther. And if I go down to 3 more orders, I get to some brand new particles that were first discovered here at CERN. These are the so-called W and Z bosons, and I'll come back to them. But the final message I want to deliver is that we can keep going to the point where we have no idea what's going on. And this is a length scale that's known as the Planck scale, and it's when gravity and quantum effects become equally important. And we really don't have an understanding of how to combine gravity and quantum. So this is a length where we just don't know what's going on. And that brings us to a very deep question. We know how to describe our everyday experience very well using physics, and we can also describe the behavior of a glucose molecule or a proton. So how is it that we can describe nature so well without understanding the length scales down below? And the answer to that question is something called effective theories. An effective theory at its heart is a very simple idea. It allows us to organize our understanding by identifying all of the particles and all of the forces that have an effect, only the things that matter for the system we're after. And as an example, here I'm showing gravity on Earth. I think many of you know that gravity here on Earth is described by a parameter called little g that tells you when you drop something how it accelerates. Little g is about 9.8 meters per second squared. So this is the effective description for our everyday experiences. But if we go far away from the Earth into outer space or around other planets, we will see that this little g emerges from something more general, the gravitational force law, and it's a law between any two masses with another constant. And this little g is built from the universal constant together with the Earth mass and the Earth radius. So this is a much more general description. But in fact, once objects start moving very quickly in outer space, planets and black holes orbiting at high speeds, then we have to go to an even more general description. No pun intended, I'm talking about Einstein's theory of general relativity. And these are the equations that govern that. But even this probably is not the final story. There's probably some quantum gravity that describes this in a more fundamental way. And the point I want to make is that Einstein's equations are an effective theory for gravity. And this simple force law is an effective theory for Einstein. And even our little g is an effective theory coming from here. So there's a whole chain of descriptions that are all valuable and important. And really what's happening is that predictions are possible because we know how to parameterize our ignorance. Down here, we can measure little g without knowing that it's built from a universal constant together with the Earth mass. But when we go into outer space, we make that deeper connection. And this is really the power of physics. Parameterize your ignorance, and as you get a deeper understanding, you'll see that those parameters maybe have a deeper meaning than you first thought. And now I've organized 4 categories of descriptions, and I want to take you through them. The first, I think, is the most familiar. That's classical mechanics. This is the effective description for marbles, for rockets, and for planets. And here's my little cartoon of a rocket flying according to F equals ma. Something that you're perhaps less familiar with is classical field theory. And this is a similar idea, but it has to do with fluids, or with electric fields, or even with the surface of a drum. So if I strike a drum, it will start oscillating, and I can think of that shape as a field. All that means is it's a function of the space and time, and it describes the drum. So here's a picture of that. This is supposed to just be the shape of the drum. After I've hit it, it's oscillating up and down, and I take a picture. That's all classical field theory is. So these are the 2 top panels, and now in the bottom, we get down into the world of quantum. Quantum mechanics also breaks into 2 sides. The left side is for things that are slow moving, and a good example is a hydrogen atom or an ion that's trapped in a little ion trap. Then we use what's called non-relativistic quantum mechanics, and this is the first thing you'll learn about in a quantum class. But when things become very high speed and relativistic, then we switch to the final form of quantum field theory. And you see the pattern here. The top 2 things are classical and the bottom are quantum. The left 2 are for non-relativistic, and the right 2 are for fields and fast-moving objects. So what do we mean when we say quantum? I think this is familiar to some of you. Quantum means that only a probabilistic description is possible. It means we can't say the electron is here or there, but we can only say if you do many measurements, it will have a probability distribution that's well determined. It will be here 5% of the time, and it'll be here 10% of the time. So that's the first rule. Only a probabilistic description is possible. And so in order to understand what's going on, all we need is a recipe for calculating probabilities of experimental outcomes. And once we have this, then we really understand how to proceed, because we can calculate the probabilities, then we can do the experiment hundreds of times and compare what happens with what we probabilistically expected. And so I'm giving a cartoon here for the trapped hydrogen atom. You see, again, the proton I mentioned earlier with the electron cloud around it. And these curves here represent the probability of where you'll find the electron as a distance from the center. This is what we call the wave function. And this brings us to the final corner, which is really the bread and butter of the work done at CERN, quantum field theory. Now for the hydrogen atom, we use the specific setup of the Schrödinger equation, and we take a potential which represents the electron. But for the experiments at CERN, we actually have one general framework. So it doesn't matter if you're describing a proton or an electron or another particle, everything comes back to the same general approach, which is called the standard model. And the standard model, you could really argue, is one of the crowning achievements of humanity. It gives an unprecedented exact description. It describes almost all collider experiments seen to date. And at its core, it has a very simple structure. So let me tell you a bit about the standard model. It's nothing other than a list of the particles in the interactions that they have, and it's organized by symmetries. And here's a quick tour of it. The first particles are the neutrinos, the leptons, and the quarks. Neutrino, it comes from the Italian word, and literally it just means little neutral ones. So these are particles where we can't see any size to them at all. So we say that they're little, and also their mass is incredibly small, much smaller than everything else. So neutrinos, neutral, very light. The leptons are more familiar, especially the electron is something that builds up also our bodies and the material around us. But there are actually three leptons, so you can think of that as the electron and its two heavier cousins. Those are the electron, the muon, and the tau, and they're really just copies of each other, but with very different masses. And finally, the quarks are the building blocks of everything else. And in particular, the quarks build up the protons and the neutrons that go into all the elements of the table, and therefore all material as we know it. But that's not the whole story. In addition to these so-called matter particles, there are four new particles that mediate the forces. They're responsible for communicating the forces between these, and they are the gluons, the photon, and the weak bosons. So first of all, the gluons are what glue the quarks together, and that's why even if I take two quarks that are positively charged, the positive charge makes them want to repel, but the strong force is so strong it can overcome that and hold together in a neutron or a proton, and therefore inside of materials. The photon, I think, is the most familiar. It's the particle of light, and it also is responsible for charges attracting and repelling each other. And the weak bosons are the particles that were discovered at CERN, and they're like very heavy photons. They're responsible for the weak force, which has to do with radioactivity. And this is the very final piece to the puzzle. It's the Higgs. And this was a particle discovered in 2012, as I'll describe more. And it's really a crowning achievement because what many scientists, including Peter Higgs, saw was that everything up here, even though it's all the particles that we had seen in nature, it wasn't mathematically consistent. There were mathematical problems in the theory, and only by adding a new particle could you fix the mathematics. And so it's really a point where we understood on a deep level the mathematical structures demanding something new, and then we saw that new thing in an actual experiment. And this was considered a big achievement because it meant we really know what's going on at the fundamental level. Now I'm going to show you lines of how these particles connect to each other. So this represents all of the interactions. The Higgs can interact with everything that has a mass. So with the leptons, the quarks, and these W and Zs. The gluon and the photon, they don't have a mass, so they don't connect to the Higgs. Similarly, the photon connects to everything that has a charge. These, and these all have electric charge. And finally, the gluon only connects to itself, so you can have many gluons sticking together, and also to the quarks. So at this point, it's pretty simple. The only thing that makes this quite messy is that the W's and the Z's really interact with a lot of things. So when I turn on all of their connections, this gives you the full story of the Standard Model. And this describes essentially all collider experiments known to date, or I should say the mathematical equations behind this picture. So here's the Standard Model, and I'm showing here Peter Higgs, who predicted this last particle that was discovered in 2012. And I would say that the Standard Model is a very effective theory. It describes a huge amount of experience, but it's definitely missing some pieces. It's missing an explanation of the neutrino masses. We now know that even though they have a tiny mass, it's not zero, and we don't have any theoretical understanding of where this mass is coming from. Also, it's missing gravity. Of course, the number one force in our everyday experience is not in the Standard Model at all, so this is a huge gap. And the third thing it's missing is dark matter. If we look out into the cores of galaxies, we can see from the gravitational effects that there's a lot of dark material that's definitely there from its mass, but it's not sending out any light. And we really don't understand what this mysterious dark matter is. So there's still a lot of work to be done. And that brings us to CERN, both the past and the future of CERN. So that's where I'm sitting right now. And I want to first just give you a basic intro. CERN is the European Organization for Nuclear Research, and the name is derived from these French words that I won't butcher for you. It was established in 1954, so shortly after the Second World War, and it was established by these 12 countries. And so this was really in the spirit of unity after the Second World War, and also European unity, that these 12 countries came together to apply technology to not a destructive cause, but to a peaceful cause of more fundamentally understanding the particles and the forces in our universe. By now, CERN has expanded. It's 23 member states, all based in or around Europe. So here you can see, and where it is exactly is right here on the border between France and Switzerland. So if I zoom in here, you can see a local map of the Institute and indeed where I'm sitting right now. And so at the risk of sharing a bit of information, I'll tell you, I live here in Ferney-Voltaire. This is on the French side, and I'm sitting right now here at CERN on the so-called Meran site. So every day when I go to work, I have to cross the French-Swiss border here. And you can also see that these rings represent huge tunnels underground, and the particles are flying through these tunnels in order to produce collisions that help us better understand nature. If you'll indulge me for 1 second, I just wanted to comment. I would strongly encourage anyone who has the opportunity to come visit someday. It's really a nice area, and this is a picture I snapped yesterday, just a few blocks from my place. So you can see that it's kind of actually a rural, mountainous area, also with lots of farming. Right now there are sunflower seeds everywhere you can look, and it's hidden in sort of this mountain farming community. Remarkably, one of the largest particle experiments, or the largest particle experiment on planet Earth. And I really have the feeling a lot of people here don't know that these tunnels are underneath their feet, but indeed they are. And if I tell you that my bike to work is about 4.5 kilometers, you can see that's in fact about the radius of this larger tunnel. And so you can see this is really a massive complex, a tunnel that's 4.3 kilometers in radius and therefore 27 in its circumference, so about 17 miles if you go all around this ring here. And currently housed in this enormous tunnel, which cuts under the French countryside, cuts under part of Geneva in Switzerland, is the Large Hadron Collider. And before telling you more about the Large Hadron Collider, I'd like to give you just a little bit of a timeline of history. I've already told you that CERN was born in 1954, and the first collider was already built a few years later in 57, and this was already digging some of the infrastructure here, not yet a full tunnel, but this is a starting picture. And the first new particles they observed were anti-nuclei. We know that for every particle, there's an antiparticle, and they could see this for things like helium, anti-nuclei. Then in the 70s, they built the first big ring, and that was called the super proton synchrotron. And in fact, that ring is still here today. And so I just think this is a fascinating story that I wanted to deliver, that this little ring was the entire CERN infrastructure in the 70s. This was the big collider. It's just now been dwarfed by something much, much bigger. This little ring was called the super proton synchrotron. It was 7 kilometers around. And this is where they discovered these two new particles, the W and the Z bosons, which help us understand radioactivity and also the electroweak force. Then in the late 80s, they were motivated to keep pushing the progress, and they dug this enormous tunnel, already finished in 1988. This is when I was 1 year old. And they started by shooting electrons around. And what they used this LEP tunnel for with the electrons was to produce many, many Z's. And I already told you about how quantum mechanics is about probabilities. So if you can produce something 17 million times, then you can really see what happens. And through these 17 million measurements, you can really understand the probabilities. And the second thing I wanted to highlight is one thing that's amazing about particle physics is you quickly go from discovering something for the first time to being a factory, producing them like it's standard procedure. So in just 5 years, they went from seeing the Z boson for the very first time that had ever been created on Earth to producing it 17 million times. That brings us into the 2000s. In 2008, they changed what they were shooting in this big tunnel. Instead of electrons, they started shooting protons, heavier charged particles. And that allowed them to discover this brand new particle, the Higgs boson, in 2012. And one funny comment I heard recently is you'll notice the big discoveries at CERN are the W boson, the Z boson, and the Higgs boson. And what I haven't told you is other particles were discovered in the US, especially the bottom and the top quark. And the joke that people say is that quarks or fermions are discovered in the US, whereas bosons are always discovered in Europe. So far, that's been kind of true. Okay, very nice. So I've told you a bit about the history and the discoveries, but I think the question that jumps out at you when you see this huge tunnel is why does it have to be so big? And the reason is to do with something called Bremsstrahlung, or synchrotron radiation. We know if we shake a charged particle or accelerate it around in a circle, it will radiate light. And in fact, this is the same principle as in a light bulb. All the charged particles are shaking in there and sending out the light. Here, the charged particles are just running around in a circle, but the fact that they're changing the direction means they also lose energy. and the sharper they turn, the more energy they will lose. So here's our master formula that says how much energy they will lose per time. These are just some constants, the electric charge and the speed of light, and these are the two factors that matter most. So what are they? Gamma is just the ratio of the energy to the rest mass. And for a concrete example, let me tell you about LEP. Remember, LEP was the electrons that were running around this big ring. Those electrons had an energy of 50 GeVs. And if you have an electron at rest, following Einstein's famous equation, E equals mc squared, the rest energy of the electron is just 0.5 MeVs. So these are our standard units of energy. And if you take this ratio, you will see that you have well over 1,000 for this gamma factor. So this is going to be a big number. Finally, this R here is just the radius of the tunnel, roughly the same as my home to work distance, and that's 4.3 kilometers. And if I plug this all in, I will see how much energy the electron is losing. It's losing about 2.2 times 10 to the minus 7 watts. So you say, okay, 10 to the minus 7, that seems like a tiny amount of watts compared to what I use at home. But of course, there are billions and billions of electrons running around simultaneously. And if you multiply that up, then you quickly get into the thousands of watts. And this is why the tunnel has to be so big. It's possible for them to supply these tens of thousands, but if I try to save some money and make the tunnel maybe half the length, then this becomes smaller, which means my P becomes way bigger. So half the tunnel means quadruple the energy loss, and then it's no longer possible. And so that's the punchline. Big tunnels are needed in order to keep the energy loss under control. And since 2008, the same tunnel is colliding protons, and because it's such a big tunnel, we can get those protons up to a 13 TeV collision energy. And this is really the highest energy that's been achieved in any collisions on planet Earth. I think there's a repeat here, same slide. And now I want to try to show you a brief video to give you an even better idea of what's happening here at CERN. Let's see if this will work. Okay, so hopefully here you're seeing the introduction to the video, and this is sort of an advertising thing zooming in on CERN, coming out from outer space, and this is the same complex I already showed you. The smaller ring is the old collider and the bigger ring is the new one. And you can see that currently, in order to get the protons into the big ring, they start from a very simple source of protons, a hydrogen bottle, and then they go through this series of accelerators. So the details aren't so important, but it's just interesting to see that they start in smaller rings and they get going faster and faster. And every time they're faster, they get shot into the next ring. So now they're in number 2 at an even higher speed, but this ring is still not nearly big enough for the kind of collisions that we want. And so you repeat the pattern again, you inject them into the bigger ring. And this is the super proton synchrotron. This was the biggest collider on Earth, and now it's just used to feed the master collider. And finally, it gets fed into the true Large Hadron Collider, and there you can see the protons running around these chains of magnets. And here, I'm going to pause for a second. We're about to see the collision, but before I show you that collision, I want to show you a couple more slides in my talk. I want to go to a scattering 101, kind of an introduction to scattering before we show the more fancy scattering that's happening in the video. So here I'm showing a sort of simplified theorist perspective of what this experiment might look like. The particles can come in from the left and the right, and they will collide, and everything you see on the top and the bottom is like a camera. It's a detector to see what happens. So now I'm going to hit go, and you see that 2 particles collide, and they land in the detector. Now, what exactly happens, we'll never know. It's probabilistic. But if I repeat this again and again, then I get an idea of a pattern forming. And so by performing this collision hundreds of times, I see a distribution, and it depends on the scattering angles, and it also depends on the energies. And this is exactly how we do particle physics here at CERN and many other places. the idea is that we can predict these same distributions using the theory. And so on the left side, you see the theory prediction. On the right side, you see the experiment. And in this case, there's something disagreeing. And this is exactly what we hope for as physicists. If something is mismatched, then it means we have something new to learn, something that we haven't yet understood. And now I'm going to show you in the video a little bit more realistic idea of those same collisions. So I'll switch back now. And I paused you right before the moment of truth. And so when I hit go, you'll see the protons smashing together in a collider detector called CMS. In the collision, you explode into many particles, and these collisions are happening all around the ring, many, many times per second. Here's another example, and you can see each collision gives you a snapshot, and this produces a huge amount of data. And so another incredible challenge at CERN is to combine all of this data and organize it. And you see these yellow lines represent data flowing from all of the different experiments and being collected in this incredible supercomputing center. This has to be copied and backed up. This is a huge IT department that's managing this, and it's a really daunting challenge. And then finally, this data flow is distributed worldwide for analysis. And so here we're going into the worldwide network. This helps you understand why CERN invented the World Wide Web. It was to organize and manage this data that's being analyzed by universities and institutes across the planet. And by looking inside of this data, we see exactly what I showed in my cartoon. We see something unexpected. And so here you see those probabilities, and it's comparing the experiment to the expected. And now let me stop for 1 second. What we're seeing here is that the purple curve represents what was expected, and this little tiny bump tells you that there's something new, something that we hadn't seen before. And this represents the discovery of the Higgs boson, this new particle that was discovered in 2012 that completed the story of the Standard Model. And so this was analyzed by both CMS and Atlas. And the final thing that we're going to see from CERN is collisions that are exploring the conditions at the beginning of the Big Bang. In addition to discovering new particles, we're also looking at the early universe effects, and these are the two main directions of CERN. And so that concludes the video. And now let me jump back to my slides, and I can then wrap up the presentation. All right, so I hope by now I've given you some flavor of both where CERN came from and also the kind of work that's being done today. Here I'm flashing the timeline again that takes us from the first collider into the super proton synchrotron, that's the little ring here, and on to the discovery of the W and the Z, and finally the Higgs. And now I want to slide this timeline along, and I want to ask the question, where is CERN headed now? Now, we do have a very concrete timeline for the next few years. Right now, CERN is in a long shutdown. It's called Long Shutdown 2, and it means that nothing is happening because people are down in the beam, in the tunnel, improving the magnets, improving the detector technology so that we can run with more collisions at higher energies. And this is going to lead to a run 3, and finally, in the late 2020s, into what's called high LUMI LHC. So we already have a roadmap through the end of 2030, where we're going to collide at really unprecedented collisions per second to collect unprecedented amounts of data to gain a deeper understanding. And then once that's finished, the future is really wide open. And so going after 2030, there's an active discussion right now about which experiments are most interesting and which direction the field should take. And I don't want to spend too much time there. I just want to encourage you to look into this if you're curious. One proposal is something called the FCC, the Future Circular Collider. And you can already get a hint from this cartoon. Now the little ring was the huge ring of the whole talk. And you see that they're talking about building something much, much larger with a circumference going into 100 kilometers. And so this is sort of a summary of the history and the possible future at CERN. initially it was only this little proton synchrotron going into the superproton synchrotron. And today we have the LHC, this 27-kilometer ring that has allowed us to discover new particles like the W and the Z and the Higgs. We don't yet know what the future holds, and one proposal is this massive 100-kilometer ring that will completely surround Geneva, run under this lake, and I think it's going to be a very interesting discussion in the coming decade to see what direction the field goes. And I don't want to give any opinions there. I just want to say it's going to be interesting and we should stay tuned. And so with that, I'll say time will tell, and thanks a lot for listening.
All right, great. Thanks so much, Max. That was awesome. So now we're going to give time for people to ask questions. There's a little bit of time delay between what the viewers are seeing and what we're seeing. So we're going to let people take a second to digest and start trickling their questions. In the meantime, I have a question for you.
Yeah.
So you mentioned that hydrogen bottle that fuels the LHC. I heard that hasn't been changed yet. Is that true since the LHC started?
Yeah, I think it's right. At least unless there was some technical issue, there's no real need to change it. And that's a remarkable thing that there's enough protons in that little bottle to supply the collider for years and years and years.
Yeah, how big is it again?
The bottle, I think, I don't know exactly, but I think order 10 or 20 liters. It's just the kind of thing that you can hold.
Yeah.
The magic there is really the magic of Avogadro's number, right? So this is the number comes from the number of carbon-12 atoms and 12 grams of carbon. And really it's the number that bridges the gap between the small things and the big things. And the number is huge, over 10 times 10 to the 26. So that means even in that bottle, there are not just billions and trillions, but over 10 to the 26 protons, and that's more than enough for what the CERN needs.
Yeah, that's amazing. Okay, so we have some questions that are starting to come in. Let me see if I can read them. Okay, so we have, I think this kind of touches at the core of our field. This is from Luis Angel Vergara Ortiz from Hidalgo, Mexico, saying, what is the smallest scale a human is able to see? And what can we see at that scale? I'm not sure if C is literal, but...
Yeah, that's a very good question. And I think it's a very deep question because you kind of have to start defining exactly what we mean by everything. So I could take one stab at how we might define things. The simplest way to interpret C is what we can actually see with our eyes. And so it's the question, what is visible light? What does that even mean, visible light? We know that light has a huge spectrum, that radio waves and microwaves are light, as are X-rays and ultraviolet, many things that we can't see. The light that we can see is in the sort of hundreds of nanometer range, around 400 or 500 nanometers. And that means that the light that's hitting our eyes is wiggling, and the lengths of those wiggles are a few hundred nanometers. So that also tells you the only things you can see with normal light are about that size. And so that's sort of represented by this. This is sort of the limit of microscopes using normal light. But then all we have to do is go to different kinds of light, and then we can see even smaller things. And CERN is sort of an extension of that. Instead of using light, you're using the particles themselves, and you're smashing them at each other, just like you would let a photon hit a bacterium. So this is a picture from a photon colliding off of the bacteria into our eyes. And if we collide two protons, then we can see things that are much, much smaller.
Yeah, sounds good. So let me, hopefully that answered the question. So we have a question from Adrian Duchesne from San Juan, Puerto Rico, asking, could it be that there is a minimum mass needed so that gravity is present?
A minimum mass so that gravity is present. So certainly we never can know for sure that anything has zero mass. All we can do is put limits on how tiny the mass can be. So when we get down to the mass of a neutrino, for example, we know it can't be zero, but we know it has to be very tiny. And connecting gravity with those tiny masses is really something we don't understand. We only understand the effects of gravity on larger scales. So I think the answer is yes. Anything could be, because our understanding is very primitive when it comes to combining gravity with fundamental particles.
Yeah, sounds good. So we have another question from Luis Angel Vergara Ortiz, again from Mexico, saying, if I want to study something related to nuclear physics and work with energy and experiments, what career could you recommend?
Yeah, it's a really great question. So there's many different ways to go. The track that I took and that Raul took is kind of the more obvious one, and it's neither good nor bad. It's just one of many options. And of course, what we did is studied physics as undergraduates, and then chose to go to a graduate school program to keep pursuing fundamental research. If you choose that path, then you'll either end up leaving the field to do something else, which is great, or maybe finding a job in academia to do fundamental research. So that's one path. And I would really stress, my perspective is, whether you do fundamental research for your whole life or only for a few years, it's still a wonderful experience. And there's nothing wrong with doing a PhD and then planning to do something completely different after. Maybe the only other thing I would add is, if you pursue a more experimental-based path, then you can also find many companies that will employ you to keep doing research. So if you work with materials, you can be on the interface that brings you into a company. Or even if you pursue a path in medical physics, there are many particle applications also in the medical world, and you could sort of combine the passions of helping people out with fundamental particles. It's also a really fascinating career direction.
Great. So we have a question from Pratishan Sarma from India. Sorry if I mispronounced your name. How do you make sure that the beams of particles will collide within the detector, such as CMS, which are at specific positions at the LHC?
Yeah, it's a really fantastic question. And I mean, the short answer is that it's just an unbelievable feat of engineering. And really, there's many engineering achievements that go completely beyond my understanding. The first thing, of course, is that they managed to make this tunnel, and in all 27 kilometers is a tube, which is a very good vacuum. So they have to have this incredibly long tube and suck out the air and keep it sealed over this huge distance. And they managed to keep not only everything evacuated, but also everything very nicely aligned. Once they've achieved that, then using a series of magnets, they can control the particles to run around. And even though the tunnel is, about the size that you can make with your hand, still the protons coming in the two different directions will usually miss each other, because these little bunches of protons are much smaller. And then the final answer to your question is that when they get into the detector, something like CMS, another series of very precise magnets can shift their position back and forth until the two beams are perfectly aligned up. And then you can, of course, see that you've achieved that alignment because you have an explosion of new particles hitting your detector. So it's really very precise machining, very precise magnets, and then tiny adjustments until you align the beams and see the collision events.
Yeah, I think this answer also ties quite well with the previous question about how to get involved if you're interested in working in an experiment like those being carried out at CERN, what career path to take. I would guess that at CERN, like at Jefferson Lab, the majority of the people working there are not physicists, right? I would imagine that there's tons of people that are engineers, computer scientists, data analysis folks. So
yeah, that's very true. And yeah, I just coincidentally 2 days ago in Geneva, I met someone from Austria who is an engineer here. And he was just so excited about his job as an engineer because he was manufacturing things that you don't build anywhere else on Earth. And the engineering challenges were very exciting. And he knew he was part of something bigger, part of this incredible experiment. So I think these jobs are very attractive. And you also get to live in this cool area.
Yeah, that's great. Okay, so we have just a nice comment from Thais Diaz Soto from Puerto Rico. Very well done presentation. It provided me a lot of insight about this side of science. Thank you.
Well, thanks very much. That's very nice to hear.
Yeah. This one is a fun question. Okay, so Joaquín Eduardo Reyes González from Monterrey, Mexico. How important will quantum computing be for the studies made at CERN?
Yeah, that's a really fantastic question. It's almost spooky because we've been talking about this all this week. It's almost like you've been listening in.
Yeah.
So the answer is that CERN is very interested in quantum computing, but it's not quite decided yet what direction CERN wants to take. So I think it's still a work in progress. The interest is very high, but just like in many other places, we don't know yet what kind of quantum computers we can really achieve, and therefore we don't know what calculations we can do with them. So I can't answer, but I can tell you people are fascinated by this, and we'll see some developments here in the coming years for sure.
Yeah, and the reason why I thought this was interesting is because Max and I just co-wrote a paper, our first paper on related to quantum computers with Juan Guerrero, which some of you might know. Oh, Juan Guerrero and Alex Turso, which some of you might know as the TAs that are in our Python for Physics class. So this is something that a lot of us are thinking about. Okay, so we have a question from Leo Cho from Taiwan. Again, if I mispronounce your name, I apologize. Are there any opportunities for high school students to engage in this type of research, either by learning more about it or working alongside with scientists?
Yes, so I think there are various opportunities. I think learning more is certainly a wonderful thing that you can do, and I would recommend, in fact, maybe I can come up with a reading list that can be circulated later, because I know I'm going to forget books off the top of my head. There's also some films that I find very informative and inspirational. One example is something called Particle Fever that really tells the story of the Higgs boson in some detail. I think it's available on streaming platforms. So it's great to get informed. And if you're really motivated to get involved, I would recommend reaching out to either universities in your area or universities that you might connect to through this program. And I know, as a young researcher myself, if a young person contacts me, I'm often very excited to come up with a little calculation project or a little programming project. So I think you'll often have some success if you take initiative to reach out to anyone in this direction. And already at the high school level, if you learn a bit of programming, for example, Python, as I know is a part of this program, then you can really start to contribute. So it's a really great idea to have in mind, even at a very young age.
Yeah. Sounds good. Yeah. So if people, the message is if people are interested in getting involved, Max can provide references, but also try to get engaged with scientists, and you're getting to meet Max and many others in this program. So don't be afraid, don't be shy to reach out to them.
Yeah, absolutely.
So, okay, so we have a question related to physics from Shirvishnu from India. Can we see new particles on building the new particle accelerator, or should we crank up the energy in LHC to see new particles? Is there a theory defined for the existence of new particles?
So as far as cranking up the energy, we would love to crank up the energy, but we really can't. And that really comes back to these equations that I showed about how the energy is lost. So if I can show this slide one more time, you remember the message is the radius of the tunnel influences how much energy the particles lose when they're running around. And for this radius, the electron bunches were already losing 57,000 watts. So as you give them more and more energy, the amount that they lose running around just from radiating every time they turn a little bit means that it's no longer possible. So we're already at the maximum energies we're allowed for this tunnel. And that's why people are thinking about building a bigger tunnel. This little tunnel here, which I say that facetiously, this is already huge, this allows us to go up to 13 TeV, and this one would allow us to go up to 100. So it would really scale us up by almost a factor of 10. And that gets, I think, into the second part of the question, which is, what can we hope to see? And that's really the big question mark that no one knows. We know that the standard model is not complete. We know that there has to be some effects of dark matter and gravity. And so we would hope that firing to these higher energies would teach us something about quantum gravity or something about dark matter. And that would probably include new forces and new particles. But there's also no guarantee that we'll see something new here. And so it's a mystery, and both theoretical physicists and experimentalists are thinking about the possibilities to really understand how to build this in the most useful way.
Yeah. I mean, are there also proposals, not just for, well, I think this would line up to like new particles, but about, I mean, doing precise measurements of decay processes of the Higgs and trying to resolve questions of whether it's a composite or not.
Yeah. Very, very, very good. So that's kind of the idea of this, what is called high Lumi LHC. So the idea is here you can already measure things about the Higgs more precisely. And as Raul already hinted, Peter Higgs predicted a particle, but what we see, we don't know if it's exactly the same thing he predicted. Maybe it has some differences. Maybe it's made from even smaller particles, which means it's composite. So it's really worth studying the Higgs carefully in the next 10 years. And that's the point of high Lumi LHC. And then another aspect of this big tunnel is the history kind of repeats itself. So in the current LHC tunnel, they started by colliding electrons, and that let them make many W's and Z's. Also in the big tunnel, they would start by colliding electrons and positrons to make many, many, many Higgses. So that's a goal both of high Lumi and of the future, is to really understand the Higgs in all of its details.
Right. So we have a question that I think also parallels a previous talk. So this is from Francisco David Luis Ruiz Mina from Monterrey, Mexico, saying, how do you exactly extract the protons? The protons are alone and without electrons? Also, thank you for the presentation. It was awesome to have an insight of CERN. And the reason why this is interesting is because last week we had a talk from Carlos Hernandez Garcia talking about how to get electrons for Jefferson Lab. So here you can give a summary of the other side.
Yeah, that's an excellent question. I do have to confess that these kind of questions start to get far outside of my expertise because I'm more on the theoretical side. I think that they use either electric or magnetic fields to strip the electrons off. So certainly inside the hydrogen bottle, there are both the protons and the electrons. And then when they come out, they need to use some fields to rip them apart. But I don't know actually how that works in any detail. It's a good question.
Yeah, I can't help you much more because I'm just a theorist, just as you, but that would have been my guess as well. So,
yeah.
Okay, so, and I'm trying to filter some of the questions because some of them get towards more of the experimental side of LHC.
Yeah, sorry guys. There are very good experimentalists you can talk to get things answered. I'm not one of them.
Yeah, maybe another time we can invite experimentalists as well from there. But okay, so here's a question. Axel Morales Buendia from Mexico City. What are your thoughts or speculations on the graviton?
The graviton, yeah, super beautiful question. I think there's a pretty broad consensus that something like the graviton must exist. And the reason is that every time we have a force, whether it's the electromagnetic force or this so-called weak force or the strong force, there's always some particle associated with it. And we would expect the same for gravity. And in fact, we even have some ideas about what the graviton property should be. So for example, these particles are spin 1. That's one of its quantum numbers is spin. And we already know that the graviton should be a spin 2 particle. And we can even write down some theories of the gravitons that give us some of the basic properties. We just can't see that particle in a detector yet. So my expectation is that the graviton must exist. The flip side to that is when we get into the regime where gravity and quantum meet, we have very little idea of what's going on. And so my intuition there could be wrong. So I will say it a little bit tentatively. I would expect the graviton to exist for sure in some way, but it could be very different than we expect because everything at these physics scales is going to be very different than we expect.
Sounds good. So we have a couple more questions. So this one, I think might need a little bit of translation. So this is from Brian Go from Indonesia. Brian has been really active in REYES, so hi to Brian. So the question is, since leptons are well known to be components of baryons and mesons, I think maybe he meant quarks, and could there be other components that construct leptons other than the Higgs boson? I think the question perhaps can be translated to, We already touched on the possibility that the Higgs is composite. Maybe the question is about, are there possibilities that any of the other particles in the standard model are composites?
Yeah,
and
exactly. So the answer is absolutely yes. At this level, we can never say with certainty that something is a fundamental particle, and that no matter how small we go, it will stay fundamental. And in fact, this is something that I like to connect to this thing in the beginning. When we're really looking far away at the size of a human, if you're looking at a human far away, then the sand next to him, you'll never see any structure. It'll look like a point particle. And at the scale of sand, the bacteria look like point particles. So everything looks like a point particle if your length scale or your measuring is not able to see it in more detail. And there's no reason for that pattern to stop. So even though the electrons look like point particles to us now, if we can measure smaller lengths or higher energies, we could see structure there. We could see structure in the quarks and the leptons. That's one of the motivations for building bigger machines or coming up with other ways to probe nature at even smaller scales. Absolutely.
Okay, so we have a few more questions coming in. One from Fernando Pagan Caban from Atlanta, Georgia, saying, everything seems to work in sync. So what would happen if something goes wrong with one of the rings? And this made me think of, maybe the question in general is, we all only hear about the success stories of CERN. Are there been like issues with the experiment at any point? I think the answer is definitely yes.
The answer is yes. Yeah, so I can encourage you to read about the history in more detail because I can only give a vague summary. But there's certainly a very famous incident in 2008, around the time the LHC was starting, that they had a malfunctioning with one of the magnets, that the cooling wasn't working properly, and that the magnet overheated. And when the magnet is working properly, it's superconducting. But if it heats, then the superconducting gets messed up, and then you have a chain reaction where you have an explosion of overheating and malfunctioning. And these enormous magnets with all the iron around them were completely destroyed and melted. And that segment of the tunnel was severely damaged by this. So this magnet malfunction and overheating basically set back the experiment by, I think, a half a year, and they had to go down and repair the significant damage. So those kind of technical setbacks happen for sure. The other kind of setback is, I think, more controversial, and some people would say it's a good thing, others would say it's not so good. And that's the fact that we've only seen the Higgs boson since we got things working in 2012. There was actually a hope that you would see a lot more new particles in addition to the Higgs. And so far, this is really the only one. So it's a very funny kind of not working. It's working in the sense that our description is working too well. The simple structure of the leptons, the quarks, and the Higgs is describing absolutely everything we've seen, and we were hoping to see a bit more. And it could be that it's just around the corner. We just have to get the energies a little bit higher. But that's been a frustration for some people. We want to see a lot new particles, and we want to see something that surprises us that we didn't expect.
Yeah, I mean, also possibilities that there's particles in this energy region that just couple weakly to protons, right? Or to hadrons in general.
That's exactly right. We can have particles all around us that are just interacting so weakly that we miss them. And the only thing you can do is build better detectors and more precise machining and come up with other clever ways to dig out those very faint signals.
Yeah. Okay, so we have maybe one last physics related question and then one comment. So the question, okay, I'll give you two more questions. Katie Lass from United Kingdom saying, could the LHC be used in any way to produce energy?
Yeah, so let's see. So far, the LHC just costs a lot of energy. I think I can't come up with a method of how that could work, but I certainly wouldn't say it means no. It just is something that, with my experience, I couldn't come up with an idea. So what the LHC can do is turn energy into mass. And that was something that we saw in the video that I didn't talk about so much. What came into that collision was just 2 protons. And when you see an explosion of particles, the mass of all those particles flying out is much more than the mass of the 2 protons. And so you might think, how is that possible? How can you create mass? And that's exactly Einstein's famous equation, this E equals mc squared, that tells you that energy can be used to produce mass. And I don't know, some people tell the analogy of it's like having 2 cars racing toward each other incredibly fast, and the cars collide, and out flies 3 cruise ships. Of course, this would be very weird because in our everyday experience, this isn't allowed. But in the quantum world, it's allowed. That a collision of 2 protons produces hundreds of particles with much more mass. So in that direction, I can say yes. You can use the LHC to create mass out of energy. To create energy, maybe, probably, but I can't come up with a good way off the top of my head.
Yeah. Okay, last question, and then we'll save a nice comment for last. So we have Shri-Vishnu again from India. Why do 3 generations of fundamental particles exist in nature? By the way, it was a wonderful talk, really inspiring.
Well, thanks very much. Yeah, so maybe I can cheat a little bit and start with an easier question, which is how do we even know that it's really 3 generations? And I like to spin that because that was also something that was seen at CERN. And that's actually visible in this little picture here. Here you see that the Z also connects to the neutrinos, and the Z can decay into 2 neutrinos. And this is really a way of seeing how many neutrinos they are, because these have such a tiny mass, and the Z has such a huge mass that it's very easy for this decay to occur. And in this run here, when LEP produced 17 million Zs, they also got a huge amount of data of how those Zs were decaying. And they could say for sure, they're only decaying into 3 kinds of neutrinos. There's no decay into a 4th neutrino. And so what that means is if there is a 4th neutrino, then its mass has to be bigger than half the Z mass, which would mean it's totally different from these neutrinos. So this is really the CERN punchline. Okay, Z can only go to 3 neutrinos, and for the pattern to be respected, it means there's only 3 families. Why there should be 3 isn't so clear. There are arguments that 3 makes more sense than 2, because it turns out that with 3, you can violate some symmetries, and with 2, those symmetries are always respected. And we actually see in nature that those symmetries are violated. So that's a very obscure thing, but you can use 3 to violate symmetries. But why not 4? Why not 5? I don't think anyone has a deep answer. It's just what we see in nature, and maybe if we keep researching, we'll come up with a more fundamental reason why it's that way.
Okay, great. And I'll just leave one last comment. This is from Chariclea Niku from Scotland, UK, saying, thank you very much for the extremely interesting and wonderful presentation, Dr. Hansen. So
thank you very much. Maybe I can reveal I'm moving to Scotland at the end of this year. So
yeah.
I appreciate getting some feedback from Scotland.
Yeah, a little Scotland love. They're coming from Glasgow. So
very cool.
Not quite. But
to Edinburgh, so not too far away.
Not too far away. Well, friend, it's been a pleasure. Thank you so much for joining us. Let me just, before leaving the last word to my friend, let me just remind you that we have more sessions coming up in REYES. So after this, we're going to have a talk that is starting right now from NASA. So please go ahead and go to that. It's going to be from a scientist at NASA Langley. So it's bound to be quite exciting. So thank you again, Max, for taking the time and joining us.
Thanks. It was really a lot of fun. Thanks, everyone.
Thanks, Roland. For all the REYES participants, go ahead and tune in, move over to the engineering channel so you can start watching the NASA LRC GLOW program presentation by Marile Colon Robles. Thanks, everyone.
Okay, I think we're good now. Bye, everybody. Take care. Thanks again.